A planet made entirely of burning ice sounds like the opening line of a myth, the kind of contradiction that should collapse under logic. Ice, by its very nature, is cold. Fire, by its very nature, consumes. To fuse them into a single state feels like a trick of language, or perhaps a hallucination. Yet astronomy has revealed that such planets are not metaphors. They are real worlds, distant bodies orbiting far from Earth, where physics bends perception into paradox. In these silent depths of the cosmos, ice does not merely freeze nor melt. It burns, radiating heat while locked in crystalline form. This phenomenon is no invention of fantasy literature. It emerges from the most precise physics we know: pressure, heat, and the strange transformations of matter under extremes. Just as coal compresses into diamond under Earth's crust, water, so familiar, so ordinary, under immense conditions takes on forms we can scarcely imagine. Laboratory experiments have shown that water is capable of becoming something far removed from liquid or solid. At certain thresholds, it exists in a state where ions slide and lattice structures stay fixed, where ice resists the logic of touch, sound, and heat. Such states remind us that what we call nature is not fixed. It is conditional, waiting to shift when the rules are rewritten by pressure and temperature. The term burning ice is often used in popular accounts to describe these states, but the phrase carries more than journalistic flair. It conveys the unsettling reality that matter can inhabit contradictions. Fire and ice no longer oppose each other as in myth or metaphor. They coexist as a physical truth. This fact destabilizes the categories we hold about nature: that cold cancels heat, that flame destroys crystal, that extremes separate rather than converge. On these distant worlds, extremes become companions, bound into a single form. Psychologists studying the mind often note that paradoxes trigger a moment of dissonance, a mental pause where expectation collapses. The same sensation emerges when contemplating burning ice. Cognitive dissonance, a term introduced by Leon Festinger in 1957, describes the discomfort experienced when holding two contradictory beliefs at once. Here, the dissonance is not inside us, but in the cosmos itself, a reminder that reality is not obliged to preserve our categories. The human brain is wired to search for coherence, but the universe itself often thrives in incoherence. Neuroscientific studies of perception offer a parallel. The Miller-Lyer illusion, for instance, tricks us into believing two identical lines differ in length, simply because of the direction of arrowheads attached. The brain insists on imposing structure even when it misleads. In the case of burning ice, we encounter a cosmic version of this illusion. Our senses scream impossibility, yet physics affirms the opposite. The very substance we sip in a glass, that freezes into cubes in a kitchen tray, becomes an alien material under the crushing weight of planetary interiors. Just as the illusion forces us to doubt the trustworthiness of vision, burning ice forces us to doubt the trustworthiness of intuition. This is why such discoveries matter beyond physics. They unsettle psychology, mythology, even metaphysics. The Norse spoke of Niflheim, the realm of ice, and Muspelheim, the realm of fire, locked in eternal opposition. In their cosmology, the collision of these two forces gave birth to creation itself. It is uncanny that modern astrophysics describes distant worlds where fire and ice are indeed fused. Science has, in a way, given material form to myth. The stories of ancient people were not literal, but they intuited something profound: that creation arises not from harmony, but from contradiction, from states that seem irreconcilable until nature forces them together. To contemplate a planet of burning ice, then, is to contemplate the instability of categories. It asks us to question whether our divisions, hot versus cold, liquid versus solid, reality versus illusion, are as rigid as we believe. For psychologists, the question becomes whether the brain itself operates by holding contradictions beneath awareness. Split brain research in the 1960s by Roger Sperry and Michael Gazzaniga showed that the hemispheres of the brain can generate competing realities, each with its own truth, stitched together only by a fragile sense of narrative. Perhaps the cosmos mirrors this very principle. Contradictory states, coexisting, appearing seamless only from a distance. 1 hour contemplating such a planet is not a matter of idle wonder. It is a challenge to perception itself. What other assumptions about matter or mind collapse under pressure? What other categories we cling to, self and other, true and false, beginning and end, might, under cosmic conditions, fuse into single states we cannot yet grasp. The existence of burning ice planets invites us into this tension. To think of them is to stand at the edge of certainty, where the ordinary rules no longer hold, and where contradictions cease to be errors and become the building blocks of worlds. Their silent glow in deep space does not wait for human comprehension. Yet once we glimpse them, once we realize that such states are not metaphor but physical law, the ground beneath intuition shifts. These planets remind us of how thin our knowledge is, how much lies buried under pressure beyond reach, and as with all things that destabilize the familiar, they pull us deeper into the unresolved, into the sense that something more waits beneath the surface, something not yet explained, not yet named, not yet brought fully into light. To understand what is meant by burning ice, one must first confront the limitations of ordinary language. The human lexicon was forged in the modest ranges of temperature and pressure available at Earth's surface. Words like solid, liquid, or gas capture familiar states, but they fail to encompass the transformations that emerge under extremes. Water, a molecule so ubiquitous that it feels transparent to thought itself, becomes radically different when subjected to the crushing weight of planetary interiors. The ice that forms in these conditions is not the brittle frost on a window, nor the crystalline snowflake that melts upon the skin. It is a substance that appears paradoxical, hot enough to glow with thermal energy, yet structurally fixed into a lattice that resists collapse. Physicists call this state superionic ice. It cannot be comfortably placed into the binary categories of liquid and solid. In superionic ice, the oxygen atoms lock themselves into a rigid crystalline framework, forming a kind of scaffolding. Yet the hydrogen atoms, stripped of their electrons, move with the freedom of a liquid, streaming through the lattice in perpetual flux. One part of the molecule is imprisoned, the other liberated. The result is a hybrid phase, crystalline order intertwined with fluidic mobility. This duality creates properties alien to ordinary perception. Superionic ice is expected to conduct electricity with extraordinary efficiency, not unlike metals, because the mobile hydrogen ions create continuous currents. At the same time, the rigid oxygen framework preserves a structure reminiscent of solidity. The term ice is retained because of that crystalline order, yet its temperature would annihilate any terrestrial conception of frost. In laboratory simulations, such ice has been shown to exist at thousands of degrees Kelvin, conditions under which steel would vaporize while maintaining its lattice. The word burning acquires precision here. The substance radiates heat, not through flames licking at its surface, but through the intense energy contained within its vibrating structure. A cube of such ice, placed hypothetically in a terrestrial environment, would not melt into water. It would instead destabilize, collapsing violently as the surrounding pressure failed to hold its atoms in order. To call it burning ice is not poetic exaggeration. It is an acknowledgement that the material defies the expectation that heat must dissolve solidity. Psychology provides a parallel in the concept of category violation. Studies by Paul Rosen and colleagues on Disgust show that humans respond strongly when familiar categories are blurred, when food is both edible and inedible, when purity and contamination seem to coexist. Burning ice produces the same unease at the level of physics. It is matter that crosses boundaries without collapsing them, both solid and fluid, both hot and crystalline. Our cognitive frameworks rebel against this, yet nature sustains it under sufficient pressure. The deeper implication is that states of matter are not absolutes, but negotiations between forces. Pressure dictates whether molecules hold their form or break apart, whether atoms flow or fix in place. In supersonic ice, the pressure is so immense that it forbids expansion into vapor, forcing atoms into positions they would never take under gentle conditions. The universe, in this sense, is a laboratory of coerced possibilities, where matter can be compelled into identities it would never assume freely. The history of science reminds us that such coercion often reveals hidden dimensions. Antoine Lavoisier, in the 18th century, shattered old categories when he demonstrated that gases once thought immaterial could be weighed, measured, and transformed. In the 20th century, high-pressure physics extended this tradition, showing that carbon, under immense compression, becomes diamond, a structure unrecognizable compared to its graphite form. Supersonic ice extends the trajectory. Water, under compression beyond imagination, becomes something between a crystal and a plasma. The material itself resists analogy, existing in a realm where metaphors strain. What makes this particularly unsettling is the realization that our most intimate substance is capable of such transformation. Water has defined biology, culture, and mythology. It is the source of life in nearly every cosmology, the axis around which civilizations turned. To discover that its behavior under pressure is alien to intuition forces a reconsideration of how much else in nature lies hidden beneath conditions we do not inhabit. Neuroscience has long studied how humans perceive stability where none exists. Visual persistence, for instance, makes a sequence of images appear continuous in film, even though the mind is assembling fragments into a flow. Burning ice is nature's equivalent, the appearance of contradiction sustained not by illusion, but by physical law. What we perceive as impossible is maintained indefinitely, if the conditions are right. The implications reach beyond physics into how we conceive of boundaries. If water can exist as a lattice of fire and crystal, what of other elements? What of consciousness itself, trapped between neuronal rigidity and mental fluidity? The line between categories is thinner than assumed, and pressure, whether physical or psychological, has the capacity to reveal hidden states. One begins to suspect that the universe is structured to conceal such contradictions until the right force uncovers them. Just as hypnosis reveals alternate states of awareness, and just as sensory deprivation brings hallucinations into waking perception, matter under pressure reveals identities that ordinary conditions suppress. The strange world of burning ice is not only a curiosity of planetary interiors, it is a reminder that reality itself is layered, with states we have not yet touched, waiting in silence until conditions push us to discover them. To reveal a state of matter that resists intuition requires not only theory, but instruments capable of recreating the unimaginable. The journey to identify supersonic ice was not a casual experiment in a laboratory glass tube. It demanded the invention of tools that could generate the same crushing pressures and searing temperatures found in planetary interiors. Ordinary apparatus would shatter under the attempt. What emerged instead were machines that themselves resembled paradoxes, delicate enough to manipulate atoms, yet strong enough to mimic the violence of worlds. At the center of these efforts lies the diamond anvil cell, a device deceptively simple in description. Two flawless diamonds, sharpened to opposing tips, are used to squeeze a sample smaller than a grain of sand. The transparency of diamond permits lasers to be directed through the anvils, heating the material while simultaneously allowing measurements by spectroscopy. In this compressed chamber, researchers can generate pressures of millions of atmospheres, conditions so alien that they can alter not only the arrangement of molecules but the very laws governing their interactions. The diamond anvil cell is more than an engineering marvel. It is an interface between human cognition and extremes that the body itself could never survive. The mind, limited to experiences of weight and warmth within narrow ranges, must rely on instruments to extend its perception. In psychology, this parallels the notion of cognitive prosthetics, tools that extend the senses, as eyeglasses extend vision, or calculators extend numerical memory. In this sense, the diamond anvil cell is a prosthetic for imagination, translating the inhuman into forms the mind can analyze. By combining compression with laser heating, researchers such as Marius Millet and colleagues at Lawrence Livermore National Laboratory were able to observe signatures of supersonic ice in 2018. They reported evidence that water, when subjected to pressures above 1 million atmospheres and temperatures exceeding 2000 Kelvin, entered a state consistent with theoretical predictions. X-ray diffraction revealed a crystalline oxygen lattice, while electrical conductivity measurements suggested mobile hydrogen ions. The paradox of burning ice had moved from speculation to experimental confirmation. The history of this discovery echoes the path of other unsettling revelations. In the 19th century, Michael Faraday demonstrated that magnetic fields could be induced by electricity, an observation that defied intuition and reshaped physics. In the early 20th century, Ernest Rutherford's gold foil experiment revealed that atoms were mostly empty space, collapsing the familiar solidity of matter into a void punctuated by nuclei. The discovery of supersonic ice continues this trajectory. It takes the most mundane of molecules and reveals a phase that destabilizes categories, neither fully crystalline nor fully fluid, but an interweaving of both. The experiments themselves were not merely technical achievements. They required reconfiguring how scientists thought about matter. Traditional thermodynamics, developed in the context of steam engines and combustion, could not adequately predict behaviors at such scales. Computational simulations became essential companions to the experiments. Density functional theory, a quantum mechanical approach, provided predictions of how water's electrons and nuclei would behave when forced into unnatural proximity. These simulations, first proposed decades earlier, hinted that water would adopt a supersonic phase under sufficient pressure. The laboratory results served as a confrontation between theory and nature, each refining the other. This interplay between experiment and computation underscores a deeper cognitive principle. The human mind often requires multiple modes of representation to grasp what exceeds intuition. Visual illusions, for instance, are resolved more readily when one can both see and touch the object in question. In the same way, supersonic ice could not be grasped through theory alone, nor through experiment alone. The coherence of the concept emerged only when mathematics and instrumentation converged. The unsettling element is not just the existence of this phase, but the fact that it was hidden in plain sight. For centuries, water was studied as if its behavior were exhausted by familiar states: ice, liquid, vapor. Only by replicating planetary interiors did its more enigmatic identities emerge. This suggests that ordinary matter harbors layers of potential invisible until coerced. Psychology has long argued that the human mind itself functions in similar fashion. Hypnosis, trance, and altered states reveal capacities that remain dormant under normal conditions. Just as pressure and heat unlock supersonic ice, contexts of suggestion and rhythm unlock unusual states of consciousness. Both demonstrate that stability is conditional, waiting for the right force to fracture into multiplicity. The experiments also carried a symbolic weight. The diamond, long associated with permanence and clarity, became the tool to reveal instability and ambiguity. The most solid of gemstones was used to press water into a form that undermines solidity itself. This inversion recalls mythological motifs, where symbols of strength become vessels of transformation. In alchemical traditions, opposites are forced together, sulfur and mercury, sun and moon, to produce something that transcends the categories of either. Superionic ice fits neatly into this pattern, a material produced by unrelenting pressure, radiant with heat, yet crystalline at its core. Laboratories continue to refine the techniques, seeking clearer measurements, higher pressures, and longer durations of stability. The brief glimpses of superionic ice in experiments raise questions about what other phases lie beyond reach. If water alone, the simplest and most familiar of molecules, conceals such complexity, what of more intricate compounds? What architectures of matter remain undiscovered, waiting to be pried open under conditions that mimic alien worlds? As the diamond anvil cells press further, and as lasers carve new states into existence, the sense grows that we are only brushing against the edges of a reality more fluid than categories allow. Each result does not close the case, but opens new ambiguities, hinting at unseen layers that might shift the foundations of what we think matter is capable of becoming. The discovery of superionic ice in laboratories did not arise from idle curiosity. It was driven by the suspicion that entire worlds may depend upon it. For decades, planetary scientists have wrestled with the enigma of Uranus and Neptune, two ice giants on the outer edge of our solar system. Their atmospheres, rich in hydrogen, helium, and methane, give them their pale blue and aquamarine hues, but their interiors conceal something stranger. Beneath the swirling clouds lies a pressure regime millions of times stronger than Earth's atmosphere, conditions so intense that familiar matter could not possibly remain unchanged. Evidence for hidden states emerged first from magnetic fields. Unlike Earth, Jupiter, or Saturn, whose magnetic fields are aligned roughly with their rotation axes, Uranus and Neptune display fields tilted at severe angles, offset from the planetary centers. Voyager 2's flybys in the 1980s recorded magnetic topographies that defied the models of simple molten cores. The geometry of these fields suggested that the dynamo generating them was not located in a metallic center, but distributed through a vast convecting mantle. Such anomalies demanded an explanation, and one possibility was the presence of a conductive material unlike anything encountered on Earth. Superionic ice offered a compelling fit. In this phase, hydrogen ions drift through a fixed oxygen lattice, enabling remarkable electrical conductivity. If vast layers of such material exist within Uranus and Neptune, they could account for the irregular, tilted, and multipolar magnetic fields recorded by Voyager. The strange geometry of magnetism in these planets might be the natural consequence of burning. Ice churning beneath the clouds. The path from observation to inference in planetary science mirrors the logic of psychology's indirect experiments. Just as researchers infer hidden cognitive states from outward behaviors, reaction times, slips of memory, or physiological responses, astronomers infer interior structures from surface fields, gravitational harmonics, and emitted radiation. Both are acts of reconstruction, attempts to chart what cannot be seen directly. The interiors of Uranus and Neptune remain beyond reach, yet their fields whisper the presence of matter under conditions we can simulate only for fractions of a second in laboratories. The scale of these layers defies comprehension. On Earth, the thickest glaciers measure only kilometers in depth. In Uranus and Neptune, the mantles that may harbor superionic ice extend tens of thousands of kilometers beneath the cloud tops, encompassing the majority of planetary volume. If the laboratory samples compressed between diamond anvils are grains of sand, the planetary interiors are entire mountain ranges composed of the same paradoxical material. Within these mantles, heat and pressure do not annihilate ice, but transmute it into something that glows with energy while remaining locked in crystalline frameworks. These planets are reminders that matter under pressure assumes roles we do not assign to it. In the human body, pressure can distort perception, as divers descending to great depths encounter nitrogen narcosis, a hallucinatory state where the familiar becomes strange. Uranus and Neptune are subject to the same principle, but at scales that transform molecules themselves into hallucinatory forms. What seems impossible, ice that burns, crystals that conduct, becomes the ordinary fabric of planetary interiors. It is not only Uranus and Neptune that raise the question. The models of exoplanets discovered by missions such as Kepler and TESS suggest that mini-Neptunes, planets between Earth and Neptune in size, are abundant across the galaxy. Their densities imply thick mantles of volatile materials, including water. If pressures are sufficient, supersonic ice may be a common feature of such worlds. In this sense, burning ice may not be rare, but one of the most widespread states of matter in the cosmos, hidden beneath layers of clouds and storms. The notion that entire classes of planets depend on a phase invisible on Earth is unsettling in its familiarity. It echoes the psychological principle of the unseen majority, the idea that most mental processes operate beneath awareness, shaping behavior without entering consciousness. Freud referred to this as the unconscious, while modern cognitive science frames it as implicit processing. Planets, too, appear as coherent entities, but their true engines lie buried and invisible, hidden in depths we can infer but not observe. The burning ice within them is their unconscious, an immense structure shaping their visible behavior from beneath. The presence of such matter alters the way we think about planetary identity. Earth is defined by its molten iron core, Jupiter by its metallic hydrogen, and Uranus and Neptune by mantles of supersonic ice. Identity in this context is not a surface appearance, but an interior condition. Just as psychology finds personality rooted not in outward performance alone, but in underlying processes, planetary science demands that we define worlds not only by what telescopes reveal, but by what pressure creates within them. The idea that pressure rewrites identity reaches back into myth. In Greek cosmology, Uranus was the sky, Neptune the sea, domains of vast and oppressive weight. Their planetary namesakes seem to live up to these legacies, harboring interiors where molecules are forced into forms both alien and luminous. These ancient names inadvertently capture the truth that beneath surface beauty lies a crushing depth, where matter is reshaped beyond recognition. Each new observation adds weight to the suspicion that the paradox of burning ice is not a laboratory curiosity, but a planetary signature. Yet the exact nature of these interiors remains unresolved. The details of their composition uncertain. Magnetic fields point in one direction, density profiles in another, and models struggle to reconcile them into a consistent picture. Somewhere beneath the blue clouds lies the answer, hidden in mantles thousands of kilometers deep, waiting to be pressed into clarity. To imagine a planet constructed of supersonic ice is to confront a contradiction that undermines the very categories by which we organize matter. On Earth, fire and ice are cast as opposites. One melts, the other freezes. One consumes, the other preserves. Yet in the depths of Uranus and Neptune, and likely across countless exoplanets, the two fuse into a single condition. The familiar relationship collapses. Heat does not liquefy, cold does not preserve. Instead, temperature rises beyond the melting point of steel, while pressure holds water in a crystalline grip. The result is a solid that burns, a lattice glowing with heat while resisting dissolution. Such a paradox forces reconsideration of what fire and ice mean when stripped of human metaphor. Fire, in its scientific sense, is rapid oxidation, but in broader terms it is the release of energy, the visible expression of heat. Ice, in its scientific sense, is a crystalline arrangement of water molecules, but in broader terms it is stability, the arrest of motion into structure. In supersonic ice, both definitions are satisfied. The material radiates energy while retaining lattice stability. Fire and ice, in this sense, are no longer antagonists, but collaborators, fused into a partnership that defies expectation. The psychological resonance of such coexistence cannot be ignored. Carl Jung wrote of opposites as archetypal forces within the psyche. Anima and animus, conscious and unconscious, light and shadow. He argued that transformation requires integration, the reconciliation of forces that appear irreconcilable. Supersonic ice becomes a natural metaphor for this principle. But more than metaphor, it is an existence proof that opposites can combine without annihilating one another. The lattice of oxygen stands as the stabilizing structure, while the flux of hydrogen provides ceaseless motion, energy, and heat. Each sustains the other in balance, not through compromise, but through enforced coexistence under pressure. In myth, worlds of fire and ice often mark thresholds of creation. The Norse envisioned Ginnungagap, the yawning void, where the icy rivers of Niflheim met the fiery sparks of Muspelheim, and from their collision emerged the first giant, Ymir. Similarly, in Hindu cosmology, the god Agni embodies fire, consuming and transforming, while Soma, a divine drink, embodies cooling, stabilizing flow. Their interaction sustains the cosmic order. These myths resonate with uncanny precision to what planetary physics now reveals, that matter itself, under sufficient duress, becomes a fusion of these archetypal domains. The unsettling aspect lies in how ordinary intuition fails in the face of such conditions. On Earth, heat melts ice because pressure is low. Water molecules gain enough energy to break free of their lattice, collapsing into liquid. Yet under immense pressure, the molecules cannot escape. The structure holds, even as the temperature rises to thousands of degrees. What would seem to be an inevitable transition, solid to liquid, becomes suspended, creating a state that feels hallucinatory. The laws of physics are not violated, but they bend in ways that strain perception. This bending of perception mirrors what psychologists describe in altered states of consciousness. Under hypnosis, suggestion can create experiences that contradict sensory input. The subject touches ice, but reports burning heat, or feels pain dissolve into numbness through the force of belief. In both cases, whether in the brain or in planetary matter, contradiction is sustained, not resolved. What seems impossible becomes possible under the right conditions, whether those conditions are neurological or physical. The coexistence of fire and ice within planetary interiors also hints at the plasticity of natural laws. What we experience at Earth's surface is not universal, but parochial, rules that apply under narrow ranges of temperature and pressure. Just as color perception is limited by the photoreceptors in the human eye, our categories of solid, liquid, and gas are limited by the conditions in which we evolved. The cosmos exposes the incompleteness of these categories, expanding them into realms that feel less like physics and more like paradoxical riddles. It is not merely an intellectual curiosity. If vast layers of burning ice exist within Neptune and Uranus, their behaviors, their storms, their magnetism, their evolution depend upon it. These planets do not operate by the rules of surface matter, but by the dynamics of this hybrid state. Their weather patterns, which can hurl winds at supersonic speeds, may be linked to the heat gradients emerging from layers of supersonic ice. Their magnetic fields, twisted and misaligned, may reflect the convective churning of a crystalline lattice infused with mobile ions. What seems like paradox at the level of matter becomes consequence at the scale of worlds. The paradox also serves as a reminder of how much lies beyond direct human experience. Consider the way early astronomers described the moon, a smooth, flawless sphere, until Galileo's telescope revealed mountains and craters. The illusion of perfection dissolved under magnification. Supersonic ice performs the same revelation, not of surfaces but of interiors, stripping away the illusion that matter is stable or absolute. The deeper we probe, the more unstable the categories become. If fire and ice can cohabit within the same lattice, it forces us to reconsider the assumptions carried into every other domain. What of biological systems under extreme environments? Microbes thriving near hydrothermal vents, combining heat and pressure in ways that mimic planetary interiors. What of psychological resilience, where trauma and creativity coexist in the same mind, producing both suffering and innovation? The lesson repeated across scales is that contradiction does not erase. It generates new forms, held in balance only by the pressures surrounding them. The more one contemplates a world built of burning ice, the more it seems less like an anomaly and more like a principle. That reality favors the coexistence of opposites, held together in states that strain the categories of perception. And if such coexistence is possible within the cores of planets, it invites the question of where else such paradoxes wait, concealed beneath conditions we have yet to reach.
Pressure is the silent architect of paradox. It reshapes matter not by altering its composition, but by denying it the freedom to adopt the forms it would otherwise prefer. On Earth, water molecules move easily between phases because the surrounding pressure is modest. A few degrees of temperature change are enough to shift ice into liquid or vapor. But as pressure increases, the range of possible states narrows. Molecules are compressed into close proximity, their motions constrained, their options reduced. Under sufficient intensity, they are forced into identities that appear contradictory, existing in patterns that would collapse without the coercion of weight. In physical terms, pressure is nothing more than force distributed over an area. Yet in planetary interiors, it becomes a force of almost mythic proportions. The weight of thousands of kilometers of atmosphere compresses the underlying layers, amplifying density until familiar forms dissolve. At 1 million atmospheres, the bonds that govern molecular structure are no longer free to behave as they do at the surface. Hydrogen ions slip their usual boundaries, oxygen lattices stiffen into rigid frameworks, and the very definitions of solid and liquid blur. The material remains water, yet it becomes unrecognizable. The psychology of coercion offers a parallel. Human identity, under ordinary conditions, expresses itself in fluid ways. Moods shift, thoughts flow, behaviors adapt. But under sustained pressure, whether social, political, or emotional, the range of expression contracts. People assume roles they would never otherwise inhabit, adopting rigid structures to survive. At the same time, certain processes slip free, manifesting in ways that appear paradoxical. Calmness under fire, strength under exhaustion, cruelty under obedience. Just as matter under pressure reveals hidden states, the mind under pressure reveals hidden capacities and distortions. What is most unsettling is that pressure does not simply stabilize, it transforms. In water, it creates superionic phases that cannot exist otherwise. In the human psyche, it produces altered states of resilience or collapse, moments when personality seems to fracture into new configurations. The lesson is the same across scales. Pressure is not a background condition, but an active force that generates forms from impossibility. In planetary science, pressure operates on a stage so vast that its consequences reshape worlds. Within Jupiter, hydrogen is compressed until it becomes metallic, conducting electricity like a wire and driving the planet's immense magnetic field. Within Earth, iron is compressed into phases that support the dynamo of the core. Within Uranus and Neptune, water is compressed into burning ice, sustaining tilted magnetic fields that could not arise otherwise. Each case reveals that planetary identity is written not in the material alone, but in the pressures that sculpt it. The mathematics of pressure reveals its merciless escalation. Pressure increases linearly with depth, but the density of the material being compressed feeds back into the process, accelerating the rise. A few kilometers below Earth's oceans, divers confront the crushing force of 100 atmospheres. At the base of the mantle, pressures reach millions of atmospheres, enough to alter the crystal structure of minerals into high-pressure phases. In Uranus and Neptune, the pressures climb still higher, reaching thresholds where ordinary chemistry fails and new regimes of physics emerge. One can sense in this escalation a kind of psychological analogy to anxiety. A little pressure sharpens focus, constrains wandering thoughts, and produces efficiency. But as pressure mounts, the system destabilizes. Behaviors that once seemed impossible manifest abruptly. The same principle operates in matter. Under small pressures, transitions follow predictable lines. Under immense pressures, matter fractures into phases that appear to mock the logic of surface intuition. What makes pressure especially disturbing as a concept is its invisibility. It exerts itself everywhere, yet it leaves no trace until a system collapses or transforms. On Earth's surface, atmospheric pressure is constant, unnoticed, yet it governs every act of respiration. In planetary interiors, its invisibility hides the violence it enacts on matter. And in human life, social pressure, though unseen, molds decisions and behaviors with the same relentless force. Pressure is the silent sculptor, shaping without acknowledgement. The burning ice of Uranus and Neptune exemplifies how pressure can produce states that feel unreal. At thousands of degrees, one expects expansion and liberation, yet pressure forces confinement and rigidity. The mind expects dissolution, yet the material responds with crystalline order. The very expectation of cause and effect is inverted. Heat, which liberates, becomes trapped. Structure, which cools, becomes incandescent. These inversions echo the psychological disorientation that arises when pressure leads to behaviors inverted from expectation. Laughter in grief, violence in obedience, serenity in chaos. In both matter and mind, pressure uncovers what stability conceals. Without it, hidden states remain dormant. With it, they erupt into existence, transforming the system into something alien yet coherent. The diamond anvil cell demonstrates this at microscopic scales, while planets enact it at astronomical ones. Both remind us that identity, whether molecular or psychological, is conditional, emerging only under specific configurations of force. The deeper question becomes how far this principle extends. If pressure can transform water into burning ice and hydrogen into metal, what forms might it force upon compounds we have not yet tested? If pressure can invert behavior in the human mind, what capacities lie undiscovered in states we have not yet endured? Each new threshold reached in the laboratory suggests that more paradoxes wait in silence, obscured by the lack of sufficient weight to reveal them. And as planetary exploration advances, as instruments probe deeper into alien atmospheres and laboratory devices compress matter into ever more extreme regimes, the role of pressure emerges not as an accessory, but as a fundamental driver of reality. Its capacity to generate paradox does not diminish with study. It expands, hinting that the universe itself may be structured less by categories of matter than by the invisible forces that compel it into unfamiliar states. The most disquieting feature of superionic ice is not only its existence, but the fact that human perception is almost incapable of imagining it. Our senses evolved to interpret conditions on Earth's surface: moderate temperatures, modest pressures, predictable phase transitions. These boundaries shape intuition so thoroughly that when confronted with states outside them, the mind stumbles. Fire that freezes, ice that glows, solids that flow. These phrases read like oxymorons because perception has no anchor for them. The fragility of perception lies in its parochial calibration, tuned narrowly to one environment and blind to realities beyond it. Consider temperature perception. The human body detects heat through specialized receptors in the skin, tuned to a narrow band of survivable conditions. A few degrees above body temperature feels burning. A few degrees below feels freezing. Yet in absolute terms, this range is trivial. The mantles of Uranus and Neptune see that thousands of degrees, conditions no receptor could survive, let alone interpret. To imagine such heat bound inside crystalline frameworks is not just counterintuitive. It is cognitively destabilizing, because perception is designed for survival, not for truth. The same holds for pressure. Humans evolved in an atmosphere pressing with 1 bar of force. At depths of 30 meters underwater, the pressure triples, already enough to cause disorientation. At 100 meters, nitrogen begins to intoxicate, producing euphoria and hallucination. Yet these are pressures trivial compared to those within planets. The diamond anvil cell simulates conditions millions of times greater than anything a diver could survive. Perception simply collapses when asked to imagine such weight. The mind reduces it to metaphor, crushing, suffocating, unbearable. But these are survival terms, not scientific ones. The gap between what exists and what can be perceived yawns wide. This gap is not limited to physical senses. Cognitive structures, language, categories, concepts are equally fragile. The very words used to describe matter betray the limits of human understanding. Solid, liquid, gas. These terms suggest discrete compartments. Yet superionic ice inhabits no single category. It is crystalline yet conductive, rigid yet fluid. To name it ice is misleading. To call it plasma is equally flawed. The labels fracture under pressure, just as molecules do. Language, like matter, reveals its instability when forced beyond ordinary conditions. Neuroscience has shown that perception is less a passive recording than an active prediction. The brain does not merely register signals. It constructs expectations and fills gaps. When those predictions fail, when what is seen defies what is expected, perception falters. This is the basis of optical illusions, where the brain insists on seeing lines bend or motion appear where none exists. Superionic ice is a kind of planetary illusion. The mind insists that heat must melt ice, that fire must destroy structure, and yet nature refuses. The fragility lies not in physics, but in cognition's insistence on coherence. Historical examples of perceptual collapse illustrate this principle. When Copernicus proposed that Earth moved around the sun, the idea felt absurd because perception insisted that the ground beneath the feet was still. When quantum theory revealed that particles behaved as both waves and discrete points, the contradiction shredded intuition. Each scientific revolution exposes the same pattern. The senses, reliable within their evolutionary niche, fail under expanded conditions. Superionic ice continues this lineage, destabilizing categories with a paradox too vast to reconcile with ordinary intuition. The implications extend into psychology. When individuals encounter contradictions in belief systems, cognitive dissonance, they experience discomfort, confusion, or denial. The mind resists the possibility that two opposing conditions can both be true. Yet in matter, as in psychology, opposites coexist under pressure. A person can love and resent the same figure. A substance can be both solid and fluid. The fragility lies in the refusal of perception to accept coexistence, demanding resolution where none exists. This fragility has consequences beyond philosophy. If scientists had trusted intuition alone, superionic ice would never have been predicted. It required abstract mathematics and high-pressure experiments to reveal. Human survival depends on acknowledging this weakness, that the senses and categories cannot be trusted when extrapolated beyond their narrow range. Only by accepting fragility can the mind construct instruments to compensate, prosthetics for perception that extend beyond the biological frame. Yet there is a darker undertone. If perception is this fragile in the face of matter, how fragile is it in the face of experience? Hallucinations induced by hypoxia, sleep deprivation, or psychedelic compounds show how easily reality can dissolve. What is seen, heard, or felt may invert, distort, or contradict itself, leaving the subject unable to distinguish truth from illusion. Superionic ice serves as a reminder that the universe itself contains states that perform the same inversion, not in the mind but in matter. The disorientation experienced by the psyche has its counterpart in the disorientation imposed by physics. The more fragile perception is shown to be, the more unsettling the universe becomes. If fire can freeze and ice can burn, then categories we consider stable may be temporary illusions. The comfort of definition, solid, liquid, gas, stable, unstable, may be nothing more than scaffolding erected by perception to make survival possible. Beyond that scaffolding, reality may be saturated with states as contradictory as superionic ice, waiting only for sufficient pressure to become visible. And if perception falters at this threshold, it invites the question of what other truths remain unseen. Not because they do not exist, but because the human mind cannot yet endure the pressure required to perceive them. What superionic ice makes clear is that matter is not exhausted by the categories known to daily life. The familiar trio, solid, liquid, gas, was once thought sufficient to encompass all forms, until plasma was added as a fourth, and now the list continues to fracture into dozens of phases that bear only superficial resemblance to their classical ancestors. Each discovery reveals that the taxonomy of matter is provisional, shaped not by the universe itself, but by the limits of experiment and imagination. The hidden states of matter are reminders that nature is not bound by language, and that beneath every definition waits an exception pressed into existence by conditions we have not yet reproduced. The most basic example lies in the polymorphism of ice itself. Even at pressures achievable on Earth, water does not crystallize into a single form, but into at least 19 known phases, each with distinct arrangements of hydrogen bonds and oxygen lattices. Some are denser than liquid water, some less so. Some are stable only near absolute zero, others at crushing pressures. To speak of ice as if it were singular is already a distortion, yet perception insists on simplification. Superionic ice represents only one extension of this polymorphism into regions of temperature and pressure far beyond terrestrial experience. Other materials reveal equally unsettling behaviors. Under high pressure, carbon, familiar as graphite or diamond, adopts exotic structures that exist only fleetingly before transforming into yet other allotropes. Silicon, so central to modern electronics, passes through metallic and superconducting phases under sufficient compression. Even helium, often imagined as inert and unchanging, exhibits strange crystallizations at low temperatures that resist classical descriptions. Each of these examples demonstrates that matter is not a fixed set of categories but a labyrinth of potentialities, each waiting for the right pressure and temperature to unlock it. The hidden nature of these states carries both scientific and psychological implications. Science reveals them only with elaborate tools, diamond anvils, particle accelerators, shockwave experiments, each extending human reach into conditions that biology cannot survive. Psychology demonstrates the same principle at another level. Beneath the stable appearance of consciousness, hidden states of the mind wait, emerging only under pressure or alteration. Dissociation, trance, hallucination. These are not failures of mind but alternative states, hidden until forced into visibility. Matter and mind mirror one another in this layered structure, in which stability conceals multiplicity. The discomfort arises from the realization that hidden states often contradict the assumptions built from surface experience. Classical thermodynamics teaches that heat increases disorder, yet superionic ice shows that under certain conditions heat coexists with crystalline order. Psychology teaches that stress destabilizes, yet under battlefield conditions individuals may achieve hyperfocused clarity. These inversions feel irrational only because the hidden states refuse to align with surface expectations. The irrationality lies not in nature, but in perception's insistence that categories remain stable across regimes. Historically, hidden states have been uncovered through failure. When experimental results diverged from prediction, when instruments recorded values that could not be explained, new phases were hypothesized. The discovery of superconductivity in Mercury in 1911 followed this pattern. Resistance did not rise with cooling, as expected, but collapsed to zero, revealing a hidden order beneath the apparent chaos of electron motion. Similarly, the discovery of liquid crystals in the late 19th century arose from the failure of organic compounds to behave as either clear liquids or rigid solids. Hidden states emerge not through confirmation, but through contradiction. Superionic ice exemplifies this principle on a planetary scale. It was not predicted by intuition, but by the failure of models to explain Uranus and Neptune's magnetic fields. The misalignment of those fields hinted at a hidden layer of matter conducting electricity in unexpected ways. From contradiction arose prediction, and from prediction, experiment. The pattern is consistent. Hidden states are revealed not when nature affirms expectation, but when it resists it. Philosophically, this reveals a universe structured less by stability than by contingency. Matter is not what it appears to be, but what it becomes under conditions. Categories are conditional, identities provisional. Water at room temperature is liquid only because Earth provides a narrow band of pressures and temperatures. Elsewhere, it may be crystalline at thousands of degrees, or vapor under crushing weight. The hidden states remind us that what we call normal is simply the outcome of conditions, not an inherent truth of the substance itself. The unsettling implication is that hidden states may dominate the cosmos even if they are rare on Earth. Most of the universe is not built from terrestrial conditions, but from extremes of heat, pressure, and density. Stars, neutron stars, black holes. Each hosts matter in states inaccessible to ordinary perception. Quark-gluon plasma, predicted to exist moments after the Big Bang and recreated fleetingly in particle accelerators, is another such hidden state, where protons and neutrons dissolve into their constituent parts. These are not anomalies, but major architectures of reality, concealed only because Earth is parochial. This expansion of possibility invites the question of how many more hidden states remain undiscovered. If 19 phases of ice are already catalogued, how many exist under pressures not yet achieved? If superconductivity and superfluidity were revealed only by accident, what other phenomena hide in regions still unexplored? Each discovery suggests not completion but proliferation, a fractal expansion of categories that resists closure. The stability of perception shrinks further with every new revelation. What unsettles most is that hidden states often violate not only expectation, but intuition's most basic oppositions. Hot and cold, solid and liquid, order and chaos. Each collapses under pressure into hybrid states. The contradictions are not errors but conditions, waiting to be discovered. The recognition of these states destabilizes the notion of reality as consistent, exposing it instead as contingent, layered, and resistant to simplification. If the universe is structured by hidden states, then perception occupies a precarious position, navigating only the narrow band accessible to survival. Beyond that band, countless other realities exist, inaccessible not because they are absent, but because the conditions to reveal them are rare. The implication is not that matter is strange only in special cases, but that strangeness may be the rule, while familiarity is the exception. And if the cosmos is saturated with hidden states of matter, it raises the deeper question of how many remain unseen, not only because of the limits of instruments, but because of the limits of the mind itself. To describe superionic ice as burning is not mere metaphor. The lattice, though crystalline, is infused with motion. Hydrogen ions migrating through oxygen scaffolding, generating electrical conductivity and radiating heat. Energy is not peripheral to this phase, but intrinsic, woven into its very stability. What appears as ice is, in truth, a reservoir of power held captive by pressure. The paradox is that confinement produces activity, that restriction fuels dynamism. In this sense, burning ice becomes not just a planetary curiosity, but a symbol of how energy hides in forms mistaken for stillness. The energies locked in such phases can only be appreciated when measured against scales familiar to human life. A single kilogram of coal releases on the order of 30 megajoules when burned. By contrast, the energy bound within the pressures and temperatures sustaining superionic ice is not chemical but structural, driven by ionic mobility and thermal gradients extending over planetary scales. Within Uranus or Neptune, entire mantles are built of this phase, each layer radiating heat and contributing to magnetic convection. The total energy bound within these crystalline mantles exceeds by orders of magnitude all the fuels ever extracted by human industry. The paradoxical relationship between confinement and energy mirrors principles uncovered in nuclear physics. Within the nucleus, protons and neutrons are bound by the strong force, so tightly that separation requires enormous energy input. Yet those same bindings make the nucleus a storehouse of latent energy, released in fission or fusion when conditions are adjusted. Similarly, the pressure that holds water molecules in rigid lattice is the very pressure that unlocks their ionic conductivity. The same constraint that prevents melting becomes the driver of heat and magnetism. To think of pressure as merely restrictive misses its generative character. It does not suppress energy but channels it. At the psychological level, the analogy is no less stark. Constraint, whether social or personal, often appears as repression, but repression itself generates energy. Frustrated impulses accumulate tension, released in sudden bursts of creativity, aggression, or transformation. Freud described this as sublimation, psychic energy diverted from one channel into another, producing cultural achievement from forbidden desire. Superionic ice, radiant beneath its confinement, is a planetary mirror of this dynamic. Its burning quality is the sublimation of energy under pressure, not its suppression. The planetary consequences of this stored energy are profound. The heat radiating outward from these mantles influences atmospheric dynamics, driving the ferocious winds and storms that sweep across Uranus and Neptune. Unlike Earth, whose weather is largely powered by solar input, these planets host systems that appear to draw vitality from within. The convection of burning ice layers sustains magnetic fields that twist and tilt, refusing alignment with planetary axes. Energy, trapped in the lattice, bleeds outward as weather and magnetism, reshaping the external face of the planet from hidden depths. This inversion, that what appears stable conceals dynamic forces, echoes in other domains of science. Earth's lithosphere, seemingly solid and immovable, is fractured and restless beneath, with tectonic plates drifting on convecting mantle currents. Neutron stars, appearing as inert spheres, conceal densities so extreme that a teaspoon of their matter outweighs mountains. The sun, seen as steady light, is an equilibrium of nuclear chaos. Burning ice belongs in this lineage of deceptive stabilities, where stillness masks violent energy. What remains difficult to grasp is the scale of this energy when extended across planetary interiors. A cubic kilometer of superionic ice at thousands of degrees embodies heat far exceeding the output of industrial furnaces. Multiplied across thousands of kilometers of planetary mantles, the energy constitutes not an anomaly, but a dominant feature of planetary identity. To call it burning is inadequate. It is smoldering on a scale that dwarfs terrestrial imagination, a fire without flame sustained by pressures that would annihilate any terrestrial structure. The fragility of perception reappears here. Energy is most often recognized when it manifests visibly, flame, explosion motion. But energy confined within invisible lattices escapes notice. Humans struggle to perceive power without spectacle. Yet planetary interiors remind us that the most consequential energies are those that smolder unseen, accumulating not in display, but in potential. The true danger and beauty of burning ice lies in its invisibility, its refusal to declare itself except through indirect effects: tilted fields, violent winds, spectral emissions. The presence of such latent energy across planetary interiors suggests that hidden phases may not only exist but dominate in shaping cosmic dynamics. Stars, planets, and even moons may host reservoirs of energy inaccessible to direct perception, yet decisive in determining their evolution. Each hidden state of matter is not just a curiosity, but a potential engine, channeling heat, magnetism, and structural transformation in ways that resist intuition. This raises a disquieting question. If so much energy can be stored in conditions invisible from the surface, how many other planetary enigmas are driven by reservoirs we cannot yet conceive? What storms, what magnetic fields, what unexplained anomalies are the signatures of hidden furnaces operating under alien pressures? To confront burning ice is to confront the possibility that the universe is saturated with reservoirs of energy we have not yet learned to recognize, much less to measure. And if energy can remain concealed in forms mistaken for stillness, then the very notion of stability in matter becomes suspect, leaving open the possibility that beneath every apparent equilibrium, forces smolder unseen, waiting for the right conditions to reveal their power. The existence of burning ice exposes not only the richness of matter, but the boundaries of understanding. Knowledge is not infinite in scope, but conditioned by the instruments, languages, and categories available at any moment. Just as pressure sculpts water into paradoxical forms, intellectual pressure, born of contradiction and anomaly, sculpts knowledge into new structures. Yet each structure carries its own constraints, stabilizing some truths while obscuring others. The limits of knowledge are not empty spaces waiting to be filled. They are active boundaries that shape what can be thought, much as the lattice of oxygen shapes the flow of hydrogen within superionic ice. Instrumental limitations are the most obvious boundary. The human body cannot survive the pressures and temperatures where superionic ice exists. Only the prosthetic reach of diamond anvil cells and shockwave experiments makes it visible at all. Instruments are not passive windows, but extensions of perception, translating alien conditions into signals that can be registered. Yet every instrument has a range, a resolution, a threshold of breakdown. Beyond those thresholds, phenomena remain invisible. Not because they do not exist, but because the translation collapses. Knowledge falters not where nature ceases, but where tools fail. Conceptual limitations are more subtle, but no less restrictive. Language encodes assumptions inherited from ordinary perception. Terms like solid, liquid, and gas are not neutral descriptors, but metaphors drawn from everyday experience. When confronted with states that resist these metaphors, thought stumbles. The act of naming superionic ice and ice reflects this constraint. The mind reaches for analogies even when they distort. In this sense, knowledge is bounded not only by what instruments can measure, but by what concepts can tolerate. Categories enforce order at the cost of fidelity, permitting survival at the expense of accuracy. There is also the limitation imposed by cognition itself. Neuroscience has shown that perception is predictive, biased toward coherence, reluctant to accept contradiction. When data resist coherence, the brain often discards or reinterprets them. Scientific history is littered with observations ignored or dismissed because they failed to fit existing frameworks. The mind prefers error to paradox, distortion to collapse. Yet paradox is precisely where hidden states reveal themselves. The fragility of perception becomes a systemic limitation of knowledge, a bias toward the familiar that resists the unknown. Even mathematics, the most abstract of instruments, carries limits. Equations can predict behaviors under conditions never tested, but only within the scope of the models they employ. When conditions diverge too far, when pressures or energies exceed the tested ranges, mathematics can generate solutions that appear plausible yet fail when confronted with reality. The discovery of superionic ice required not only theory but experiment, because equations alone could not resolve whether the predicted phase was stable. The limit here is not ignorance but dependence. Knowledge requires the convergence of abstraction and material verification, each correcting the distortions of the other. The limits of knowledge extend into the psychological comfort zone of the knower. Confronted with states that invert intuition, the mind often retreats into analogy or myth. Ancient cosmologies explained fire and ice as primordial opposites, forces locked in eternal struggle. Modern science dissolves the myth, yet finds itself confronting a state where fire and ice coexist, as if the myth had anticipated what reason could not. Knowledge circles back into archetypes when categories collapse, revealing that imagination often grasps paradox before logic does. Yet reliance on myth is itself a limit, a concession to the insufficiency of direct comprehension. The unsettling truth is that limits are not incidental but structural. Every advance of knowledge expands the field of the unknown, as new questions proliferate from each discovery. The identification of superionic ice did not resolve the mystery of planetary interiors, but multiplied uncertainties. What are its precise properties? How stable is it across varying pressures? How does it interact with other compounds in the mantle? Each answer destabilizes certainty, creating new peripheries of ignorance. The horizon of knowledge is not a line receding into distance, but a fractal edge, endlessly elaborated as one moves toward it. This dynamic reveals a paradox of epistemology. Knowledge is built on the discovery of its own insufficiency. Each hidden state of matter reveals not completion but incompleteness, not mastery but exposure. The more science uncovers, the more it exposes the contingency of its categories. To know is to confront the limits of knowing, and to continue despite them. The pursuit is not toward closure but toward expansion, each limit transformed into a threshold for further pressure. What makes the limits of knowledge most unsettling is that they are not fixed. Just as pressure changes the identity of matter, intellectual and cultural pressures change the boundaries of what can be known. A society that denies paradox suppresses discovery. A society that tolerates contradiction fosters it. Knowledge is not universal but historical, shaped by the conditions that permit or forbid its articulation. The recognition of burning ice depended not only on instruments, but on a culture willing to imagine that matter could exist in paradoxical states. Without that willingness, the phase would remain hidden, unacknowledged despite its reality. To confront the limits of knowledge is not to despair, but to recognize that reality exceeds perception, language, and theory alike. Each discovery opens not a path to closure, but a widening gulf, a recognition that beneath every known state may lie another, waiting under pressure, concealed not by absence, but by inaccessibility. And if the structure of knowledge mirrors the structure of matter, layered, pressured, contingent, then one must ask how many thresholds remain beyond reach, not because nature is unwilling to reveal them, but because the mind is not yet prepared to bear the pressure of their truth.